Hello everyone, I am Siddhartha, a PhD student at Department of Electrical Communication Engineering, Indian Institute of Science, Bangalore. Today I will present on Tensor Canonical Correlation Analysis and Graphs. This is a joint work with my PhD advisor, Dr. Sandeep Prabhakar Chipuri. We start with an introduction to the problem. For that, consider two data sets that corresponds to the two views of the common source. In particular, we have an image data from n subjects in view 1 and the wavelet features of the similar subjects in view 2. Data in view 1 lies in dimension D1 and data from view 2 lies in dimension D2. In practice, the dimension of these data sets are high and has a lot of redundant information. So given such a page data, now we are interested in finding the common low dimensional data dimension small d very much less than minimum of capital D1 comma D2 by exploiting the correlation between these paired data sets. Canonical correlation analysis is a dimensionality reduction technique that often exploits the relation between two vector valued datasets to obtain the common low dimensional data. Once we obtain a common low dimensional data, this can be used to perform a machine learning task like clustering and classification. Now we see the mathematical model for CCA. For that, consider two data variables xi comma yi of dimensions L comma m collected from different views of a common source. To obtain a common low-dimensional subspaces, also known as canonical directions, CCA solves the following optimization problem, which tries to minimize the distance between the projected low-dimensional data variable, also known as canonical variates. U transpose X corresponds to the canonical variate of the first view, and V transpose Y corresponds to the canonical variate of the second view, and the objective function here minimizes the distance between these canonical variates. Further, the constraints on U and V here enforces the canonical variates to be correlated within the set and uncorrelated across the set, where Sx and Sy here are the sample covariance matrices defined as follows. Further, by expanding the terms in the norm and introducing the new variables as U tilde and V tilde, the optimization problem modifies to a maximization problem with an unitary constraints on U tilde and V tilde. Solution for U tilde and V tilde are obtained by computing the leading kappa singular vectors of S that is defined as follows, and kappa is the dimension of the latent variable. Further, to obtain the canonical directions from U tilde and V tilde, we use Sx power minus 1 by 2 times U tilde star and Sy power minus 1 by 2 times V tilde star. CCA problem discussed till now is effective in handling the vector value data. Further, to extend CCA to handle multidimensional data such as image data or Silhouette data, it requires vectorization. Vectorizing the data often destroys the structure present in the data. For instance, vectorizing the image data destroys the spatial structure. In contrast, our data model using tensors preserves the structure and captures the interactions among different directions. Further, to model the connection between the similar subjects in multi-view data while finding the common low dimensional representation, we model the data using graphs with nodes as subjects, and the connections are edges placed based on the similarity of the subjects. Coming to the prior art, we divide the state-of-art algorithm based on two aspects: algorithms that preserve structure in the data and algorithms that preserve the graph structure in the latent variable. CCA is a vector value dimensionality reduction algorithm that doesn't preserve both the structure and graph structure while finding the canonical directions. Graph canonical correlation analysis is also a vector value dimensionality reduction algorithm, but it accounts for underlying graph in the low dimensional data while finding the canonical directions. 2D CCA, PCCA are the variants of CCA to handle multidimensional data that effectively preserve structure in the data while finding the canonical directions. But they doesn't consider the underlying graph structure in the latent variable. In contrast, our proposed approach, TGCCA, preserve both the structure in the data and the graph structure in the latent variable while finding the canonical directions. Proposed method further generalizes the TCCA algorithm to handle higher order graph data. Now we review the basics of tensors. Tensors are multidimensional arrays. Order of a tensor represents the number of modes or dimensions of a tensor. For instance, a third order tensor is represented with X and has 3 modes. Slices are the two-dimensional cross sections of the tensor. Figure here shows the lateral, frontal, and horizontal slices of a third order tensor. Matricization, also known as unfolding or flattening, is the process of reordering the n-way array into a matrix. Mode factorization is denoted by xn and has the mode fibers to the columns of the matrix. Tensor mode product is similar to matrix product. The difference being tensors are now multiplied with the matrices along the mode specified. Here a third order tensor X is multiplied with 3 matrices along the mode 1, mode 2 and mode 3 that results in a tensor of dimension kappa 1 times kappa 2 times kappa 3. Further, an operation similar to a matrix product is defined for a multiplication of two third order tensor named T product. So if X and Y are following dimensions, then T product results in a tensor of dimension L1 times L times L3. We define an identity tensor as a tensor with a first frontal slice as an identity matrix with dimension kappa times kappa, and the rest of the slices have entries close to 0. With this background, now we define tensor canonical correlation analysis that is effective in preserving the structure in the data and handles the higher order data. For that, consider two multidimensional data variables xi, yi with n observations. TCCA finds the canonical directions by minimizing the distance between the low dimensional representations, also known as tensor canonical variates. Here, Cxi is the tensor canonical variate of U1 and Cii is the tensor canonical variate of U2. Tensor canonical variate Cxi is obtained by projecting the first view xi with the canonical directions across the unshared nodes. Since xi has 3 unshared nodes, we have 3 canonical directions multiplied across mode 1, mode 2, mode 3. Similar is the case with the second view. The constraints on the canonical directions are U1, U2, U3 and V1, V2, V3 here enforces the canonical variates to be correlated within the set and uncorrelated across the sets. TCCA explained earlier does not consider or preserves the underlying graph structure, the latent variable, while finding the canonical direction. To circumvent this, we propose a following regularizer that account graph structure, the latent variable. To do so, we view the tensor canonical variates as the attributes associated with the nodes in the graph G, represented with a weighted adjacency matrix W. The I, jth entry of W, denoted by Wij, is a non-negative real number which denotes the weight of the edge between node I and node J, and is 0 there is an edge between, no edge between them. The penalty Hg, which also depends on the canonical subspaces UI and VI, ensures that the low dimensional representations of the data corresponding to the neighboring nodes with larger weights are similar to each other, and the low dimensional representations corresponding to the nodes that are not connected are penalized such that the Euclidean distance is large. Drawing the connection between the canonical variates and the graph, we now present our problem of TGCCA, which preserves structure in the data while inducing graph structure in the canonical variates. To do so, TGCCA solves following optimization problem with objective function containing two terms. First term minimizes the Euclidean distance between the canonical variates as TCCA, whereas the second term is a graph regularizer that promotes the smoothness of the tensor canonical variates over the graph G. Lambda here is a hyperparameter that controls the smoothness. Constraints on the canonical directions plays a similar role as explained in TCCA. Optimization problem defined in TGCCA is non-convex due to multilinear product in the objective function and the constraint. To circumvent this, we propose an algorithm based on alternating minimization. Where the idea here is to find a pair of canonical directions across one mode, we fix the canonical direction across the other pairs and project the data. For instance, to find the canonical direction across U1 and V1, we fix the canonical directions U2, V2 and U3, V3 and we project the data. Here xi hat and y hat are the projected low dimensional data by using the canonical directions U2, U3 and V2, V3. Once we obtain the projected multidimensional data, we unfold this across mode 1 and solve the following optimization problem with canonical directions as U1 and V1. Our modified objective functions are represented with the f hat as follows and hg hat as follows. Constraints here play a similar role as explained in CCA. Expanding the terms in norm and introducing the new variables u1 tilde and v1 tilde, the objective function modifies to a trace maximization problem with the unitary constraints on u1 tilde and v1 tilde. The solution for u1 tilde and v1 tilde are obtained by computing kappa 1 leading singular vectors of r plus lambda g, where r and g are defined as follows. Further, to obtain the canonical directions across mode 1, we use rx power minus 1 by 2 times u1 tilde and ry power minus 1 by 2 times u1 tilde. Once we obtain the canonical directions across first mode, we fix these and the directions across third mode to find the directions across second mode. For finding the canonical directions across third mode, we fix the canonical directions across mode 1 and mode 2, and we repeat this procedure till convergence. Now we validate the theory developed for TGCCA on two image datasets, Yale phase database and UMIST phase database. Experiments on Yale phase database. Yale phase database contains images of 28 subjects under 9 poses, and each pose is captured under 64 illuminations. In our experimentation, we consider a subset of the database with 3 poses from every individual. We further downsample each image to the dimension of 50 times 40. Figure here represents sample phase images of 2 subjects under varying poses and illuminations. To obtain multiple views with tensor representation, we use Garber features with 5 scales and 8 orientation for view 1 and 8 scales and 5 orientations for v2. Graph is generated using cosine similarity, where the elements of matrix W are computed using Z, that is obtained by concatenating the data from 2 views. Once we obtain multiple views, we divide the data into probe and gallery set, also known as training and testing sets, depending on the number of illuminations considered per subject. We use the proposed algorithm to obtain the canonical directions that are used to obtain the low dimensional representation of the data with the sizes kappa 1 and kappa 2 and kappa 3 as 5. Once we obtain the projected data, we use KNN classifier, k is equal to 1, trained using probe set and tested using projected gallery data. Classification accuracy defined as the ratio of correctly classified images to total number of images are evaluated by varying the size of probe and gallery set, where for each probe and gallery set, 5 independent trials are performed and average and standard deviations are reported. To evaluate the convergence of the proposed algorithm, we plot the objective function with iterations, where it is clear that with the increase in iteration, function value decreases and saturates. Further, our proposed technique outperforms the state-of-art algorithms as it preserves both the spatial and graph structures underlying the data. Now we perform our experiments on UMI phase dataset. UMIST is an image dataset that contains images from 20 subjects, and each subject is captured under 18 poses. To obtain multiple views, we consider the data for the first view as the downsampled images, and the data for the second view is obtained by considering the wavelet features of the downsampled images. The graph is constrained using cosine similarity as explained earlier. Once we obtain 2 views, we randomly select 7 from the available for training and the rest of them for testing. Then we follow the similar procedure as explained earlier to obtain the low dimensional representations for both the training and testing data using the dimensions of kappa 1 and kappa 2 as 8. We use the KNN classifier with k is equal to 1, trained using projected trained data and tested using the testing data. Mean classification accuracies and standard deviations are reported with the value of hyperparameter 1 into 10 power minus 3 for TGCCA. It is clear that proposed technique outperforms the other techniques due to the inherent advantages of preserving the spatial and graph structure underlying the data. Following the conclusions, we proposed a dimensionality reduction technique for 2 variable multidimensional data, which preserves structure in the data and underlying graph structure in the latent variable. An algorithm based on alternative projection is proposed for finding the low dimensional subspaces. Proposed algorithm is tested on 2 real phase datasets for classification tasks. Thank you.